Okay, good morning, everyone. We're going to be starting today by briefly doing, giving a couple of the pretty pictures I alluded to at the end of last lecture that relate to SVMs, right? So, kernels rather. So last time we talked about support vector machines being a natural way to think about generalizing finding linear separators from thinking about simple logistic regression, right? And they were sort of inspired, and the last function that they aimed to minimize was inspired by this idea that what one often wants to do is pick a hyperplane that separates points with as much space or as much margin around that separating hyperplane as possible. Okay, so one of the sort of challenges we faced when we were thinking about drawing a hyperplane that separates points with as much distance from the boundary as possible is that in many cases we won't have a data set that is perfectly linearly separable, right? And we had sort of two techniques to address that, one of which was sort of generalizing our notion of margin, right? And just thinking about the penalty of violating the margin as being incorporated into our loss function, right, with these slack variables. And the other was to think about lifting our data into some different space, right? Taking some map phi and applying it to each of our data points, and then thinking about finding linear separators in that different space. So we're going to talk a little bit more about that today before moving on to another topic. So we'll start by reminding ourselves what a kernel is, right? A function k is a kernel for a map phi if k applied to two vectors in Rd is functionally equivalent to taking each point x and x prime, mapping them by phi, and then taking the dot product between those two. Great. Okay, so here's a simple example of a kernel that you might have seen pictures like this appear perhaps in the textbook, and if you're sort of trying to understand what kernels are, these are some of the first kinds of pictures that show up when you do Google searches, right? This idea that maybe you have like a fairly linearly discrete boundary between the points that you're wanting to label red and the points you're wanting to label blue, but that separation is not linear in the current representation of your data. If that's the case, okay, then what you normally want to think about doing is thinking about whether or not there's some way to transform your data into a space where there is a nice linear separating hyperplane. And here, this particular map phi does that quite nicely, right? And if we look at this three-dimensional space that we've mapped our data into, right, there's suddenly a nice linear separating hyperplane. If you can imagine projecting that into 3 dimensions, it's hard to draw 3D on a 2D surface. But the point is that if you use fairly simple maps, you can often take data that exists in 2D and then transform it, maybe even just into another 2D representation of the space, but in this case 3 dimensions, and suddenly the data is linearly separable in that transformed space. Okay, and there are many examples of these kernel functions which do the appropriate thing or do a nice thing transforming your data into something that may not be nicely linearly separable in one space, but once transformed becomes nicely much more separable. And here are several examples of such kernels. And we're going to focus a little bit more on this one, because it's so prevalent in practice, and if you're thinking about many different problems, this particular kernel comes up all the time. But I want to mention, right, We talked about kernels being applicable, not just the kernel trick being applicable, not just to SVMs, but more broadly to many, many different techniques in machine learning. And one of the things we talked about last time was using the kernel trick for regularized least squares. And we sort of waved our hands and said, it's important that you think about regularizing, otherwise you'll overfit. And we've sort of given a number of different examples of why one generally needs to think about regularization and think about how much data you actually need to do a good job generalizing. So we'll talk a little bit more about that specifically when we're thinking about kernels, and for a moment when we're thinking about kernelized regularized least squares. Okay, so remember that one of the ways we can think about a kernel method is not explicitly thinking about picking some function in this higher dimensional space, but instead thinking about some weighting over our data points, right? One of the first pieces of the kernel trick is showing that the thing we're trying to optimize for, W in the case of linear models, that thing actually can be represented as a linear combination of data points that were in our training set. So that's what these alphas are right here, okay? And unfortunately, if you think about lambda being equal to 0, right, and ignoring this term here, which is the regularization term, unregularized kernelized least squares can overfit data because one can always choose this particular weighting. And we'll give you another example, not specifically thinking about least squares, but a particular kernel that can do quite a bit of overfitting if the parameters aren't tuned appropriately. Okay, so as I mentioned, we're going to talk a little bit more about this kernel, right? The kernel that appears very, very frequently in practice, right? The radial basis function kernel, or the RBF kernel for short. Right? And it has the following form, right? It looks at the distance, the L2 distance between two vectors, squares that, and then does some exponential transformation with respect to that distance. And notice that I've introduced this kernel without explicitly saying what map phi this is a kernel for. I'll give a little bit more information about that on a following slide. But you know, one can think about using this kernel even sort of ignoring the map for which it is a kernel. So this kernel does something fairly interesting. Kevin's face showed up in the chat. That's a very interesting feature I haven't seen before. Okay. Okay, so what the radial basis function kernel does is something somewhat non-intuitive, right? But if you look at this left-hand plot says if we're thinking about applying the kernel to some x, right? Really, that's you can think about applying the kernel to x and each of our training points xj, right? And as a function of the distance between x and xj, we're seeing these different bumps, right? And these different bumps, this is x. This might be x1, this might be x2, x7, right? Each of these bumps represents the kernel applied to some x on the x-axis and one of our training data points. Which then corresponds to, if we're thinking about our function being the linear combination of our kernel applied to x and each of our training points, then weighted by alphas, right? That just looks like this particular function right here. Okay, so what is this kernel doing? Well, it's not totally intuitive, but one of the things that's really critical to think about, I didn't say anything about where this sigma was coming from. Right? And that's going to have a lot to do with how this kernel behaves, right? As is sort of indicated by these plots, right? So if we have a particularly small, also sigma, which we normally think of, bandwidth is a word that's used when thinking about this kernel. That's what's usually referred to as sigma, okay? And as we vary the value of sigma from larger to smaller, that's going to have a lot to do with sort of how wiggly the function we're learning is going to be allowed to be. Okay? So the leftmost plot has sigma 0.01, right? And this one's 0.1, and this one's 1. Right? So as sigma grows larger, that's going to be a nice example of the bias variance trade-off we've talked about before, right? Larger sigma is going to correspond to better, lower variance, but higher bias, and the opposite being true for smaller sigma. Now, sigma isn't the only thing that affects sort of how much we're trading off bias and variance, right? Because we were also thinking about the regularization parameter, which we talked about briefly before, right? So if we're actually thinking about optimizing something that also has this regularization parameter, lambda, the larger lambda is, sort of the less our kernel is going to be able to overfit for data. Right? And that's sort of the intuition we have for regularization often is like the more weight we place on the regularization term, the harder it's going to be to perfectly fit our training data, but the better we should expect the behavior we see in training to generalize to test. Right? And this is another example we see here, right? So if we both decrease, if we both increase sigma and increase lambda, we'll notice that we actually see a much less overfit curve right here. Okay, so this previous slide was thinking about using the RBF kernel in something like regression, right? For example, if we were thinking about least squares, regularized least squares, what does it mean to use the RBF kernel for classification? And a short answer is that it allows, like we were initially thinking, for highly nonlinear separations of data in our original feature space. And here's a particular example, right? And depending upon how you weight your lambda, you'll see different different nonlinear separators appear when you're doing this optimization. Okay. So I mentioned briefly before that this kernel function we can sort of think about independent of what map it is a kernel for. But there is a function for which it is a kernel. And this is what that function looks like, right? So the ith coordinate, so remember what it means for this to be a kernel of this map, KUV has to be equal to phi of u taking the dot product with phi of v, okay? So if we think about what phi would actually satisfy this for a k, this particular term expresses that. And this is just representing the ith coordinate of that map. And we haven't said anything, or at least this particular slide doesn't say anything about how large I might be. And the reason for that is that phi is actually an infinite dimensional map, right? It maps from RD into a space of infinitely many dimensions, right? We actually want to think about phi as having, not being representable in finitely many dimensions. Right? And then if you think about what the dot products of phi look like, the following derivation gives you some intuition for what that looks like. Okay, so, right, and these are both in RD, and these are in, you know, okay, so you might be thinking about why thinking about a map that maps our points from RD into infinitely many dimensions is a good idea, right? It should make it easier to separate our points, the linear separator in an infinite dimensional space, if you were thinking about using a linear separator. But we've traded one beast for another, right? We've gone from a set of data, which may not have been linearly separable in RD, to a set of points that's maybe linearly separable in a much higher dimensional space, but the space is much higher dimensional. And we've sort of waved our hands at you a lot and suggested that the way we argue about generalization, or one way to, a good rule of thumb to argue about generalization, is to think about sort of the number of parameters or the dimensionality of the set of functions you're optimizing over as being a good rule of thumb for the thing that governs how much you're going to overfit relative to the number of training data points you have, right? But that is really just an approximation, and it's not always the best way to argue about whether or not you're going to overfit. And as we talked about at the beginning, one of the motivations for using support vector machines was thinking about maximizing this margin being a good idea if we don't have a really strong understanding of what our data generating process looks like. And there's actually a nice way to argue that if you maximize your margin can be the thing you use to argue about generalization, as opposed to the number of parameters of the function you're actually optimizing for. Okay, so if you do regularization and you actually guarantee you can show something about the margin of the classifier you've learned, then you can argue that you won't overfit as much as you might expect in an infinite dimensional space. Right? R here, by the way, is just, you know, when we take X and we map it to phi of X, distances need not be preserved. So if you look at basically and margins won't necessarily be preserved either, right? So it's important to think about the maximum L2 norm of X, and that's R, okay? So scaling your data up will increase your margin, but it won't make the problem any easier or harder, which is why the relationship between the max L2, the max L2 norm of any vector we might see, and the margin sort of interplay in this way that has to do with regularization. Okay, so that's all I wanted to say, but does anybody have any questions about that before we move on?
Sorry, could you please remind us what the margin is here?
Yeah. So if we're thinking, let's think about the setting where everything is separable, right?
I did not hear it.
Yes, sure. So the question was, can you remind us what the margin is? So I'm going to draw an example where things are linearly separable. Okay, so the margin of this classifier is equal to this distance right here, okay? Right, so it's equal to the distance between the closest points on either side and the actual linear separator. Okay, any other questions? All right, with that, I will turn it over to Kevin.
Okay. Thanks, Jamie. Well, good morning, everyone. I don't know if you're feeling like me, but I'm feeling a little tired today because for the first day in about a week, I was not woken up by the sun. I had to wake up by my alarm. It's pretty crappy outside right now. Not super thrilled about it, but good news. We're talking about exciting topics today, some of my favorites, so we'll stay awake. Only the host can share in this meeting. Okay, I have to make myself host.
I think you should be able to share now, even without making yourself host. I think I just clicked on the appropriate thing to allow that.
Good. Okay. Thank you. So today we are talking about neural networks. So Jamie just got done talking about kernels, and for a little history, so I think it was in the 50s when the perceptron was first invented. And the perceptron was basically a linear classifier. It was a very simple, it was a linear classifier and a particular algorithm that came with training that classifier. And at the time, people heralded this discovery as it is an amazing invention that will soon be taking AI by storm, and we'll have robots taking our jobs, and everything will be wonderful or dystopian, depending on how you feel about that particular issue. And so this high lasted for a few years until someone came up with the very, very simple example where they realized, well, if I have a linear classifier, if I just have data like pluses and minuses, and I have something like this, 2 pluses, like this, there is no linear line that can separate this data perfectly. It cannot separate it into, you cannot put 2 pluses on one side of the line, 2 minuses on the other side of the line. This is known as the XOR function. And the linear classifiers cannot learn XORs. And this sort of Boolean logic is how it was very in vogue and very popular to think about these kind of functions because all computers are based on Boolean logic. And so if this perceptron or linear classifier could not learn simple Boolean logic, for one thing, it was not Turing complete, but it could also not learn even the simplest of functions, like XORs and things. And so there was a major sort of concern over this. And so people started thinking, well, what else can we do? And one thing we started thinking about was, well, as Jamie was describing before, we can project up to higher dimensions. And if we project up to higher dimensions, then we can learn in that space. If we add x1, x2, and then, if this is x1 and this is x2, if I add x1 squared, x2 squared, x1, x2, all polynomials, I can then learn again. One issue with this, though, is that, you kind of have to be able to visualize your data and you have to be able to see it. And so that became very sort of troubling because, how did you actually make these phi maps? Now, Jamie described kernels, which is a way to do this sort of automatically. Instead of choosing the phi map, you choose the kernel function, which is sometimes easier to use. And this idea was always around, and it kind of took very, very popular machine learning. But before kernels, there were neural networks, and they were basically the second idea after the perceptron to try to learn non-linear functions, these more squiggly sort of things, these more sort of non-linear decision boundaries and things like this. And so we're going to talk about them today. And then and then by the end of this sort of section, we'll see why they sort of had their boom between the 50s and say 80s, and then the AI winter came, and then no one really wanted to talk about neural networks, so it was kind of a backwater for about 20 years. And then now they are the hot thing again, and I'll try to allude to some of this history over the period of this lecture to give you why neural networks have had such a storied history in machine learning. But first, so what is a neural network? So a neural network is really just a simple extension of what you already know. So let's just talk about binary classification with logistic regression, okay? And so I'm going to draw this in a particular way. So let's say that let's call x naught equal to 1. We have some feature vector, x1, x2, x3. So we're in 3 dimensions. This x naught is just always going to be our bias unit. So it's always going to be a 1. And then, and so this is, sometimes we've called this theta naught, or sometimes we've called it b, is just the offset. And so a linear classifier of logistic regression was basically, we do this inner product of theta transpose x, and then push it through the sigmoid, which is g, which I will call g throughout this lecture. And just to remind you what this looks like, basically it's a map that maps basically negative infinity to positive infinity to just 0, 0, 1. It just maps negative infinity, like negative 10 maps to 0.01, 5 maps to 0.1 or something like this, to 0.9. It's just some map. And what we were doing in linear regression, or logistic regression, was exactly this. We were just learning some function, g of theta transpose x, where it was linear decision boundary. Where does g of theta transpose x go through 1/2? That's exactly where the decision boundary is. And how I'm going to visualize this is, or one way to visualize this is through a graph where we have the bias unit, and then this process, each node is an input value. It's the value of x1, x2, x3. We're in 3 dimensions. And then the weights are on the edges. So wherever you see an edge, that's a weight. And when we have multiple nodes attached to edges going into another node, that's going to be called the inner product. And so this sort of notation here is basically taking the inner product between the theta and the x, which is here, and then pass through some nonlinearity, such as the sigmoid in this case. And so we get this function h theta of x, which is really just taking the inner products of theta with x and then mapping it through this nonlinearity. Okay, so this is logistic regression, nothing new here. A neural network takes this basic concept and just repeats it. So if we look at, say, A3 here, what's going on here is we start with our initial feature vector of x1 through x3. We have our bias unit x naught equal to 1. That's always pegged at 1. And now A3 is equal to g of the sum of I equals 0 to 3 of xi and then theta I, and I'll just say this is theta of 1. Theta of I, let's say 3. And then we repeat that, each one of these is going to, and then this guy is going to be equal to g of I equals 0 to 3 of xi theta I 2. So this theta is in R4 by 3. No, sorry, 3 by 4. Because it's hitting my x vector, which has 4 dimensions, these 3 input dimensions plus a 1 vector of 1s. And then it's outputting to just these 3 dimensions here, which I'm calling A2. And so I can write this succinctly as A of 2 is equal to G of theta of 1 of X. So that's these guys here. And then this guy right here is equal to G of theta of 2 times A of 2. Okay, where then theta of 2 now is mapping to a one-dimensional space, this last node. So it'll be from a four-dimensional space, from a four-dimensional space, so it's 1 by 4, because it's taking in these four numbers as input and mapping it down to just a single output, and so theta 2 is that. And so I can repeat this, and just to write this out a little more clearly, we have this same network. The A of 2, this guy right here, A of 2, 1, is equal to G of these matrices, where theta, this big capital theta with superscript J, is just the Jth weight matrix. And I'm just mapping all these inputs to outputs along each layer. And so this whole network, again, every edge is a weight. And so if I have this input layer, which is three-dimensional, and the output layer, which is three-dimensional, I guess I lost my bias here, x0. And then my also a1, 0, or 0, 2, whatever. Then this whole network is parameterized by just these weight matrices of theta 1 and theta 2 with the appropriate dimensions. Okay. And so in general, we can repeat this many, many times. And so we'll have in this function g that is applied to this vector is applied element-wise. So the way this works, I've now dropped the 1, this bias term, because I can just put it into x without loss generality. And so I start with my input x. And then for the second layer, the weights at the second layer, or the outputs of the second layer is a vector. And it's the product of a weight matrix theta of 1 times a of 1. So now I'm getting theta of 1 times a of 1 is going to be a vector. And now I apply this nonlinearity g to all the elements of that output, and I call that a of 2. And for the purposes of just this lecture, I've been using just this nonlinearity of the sigmoid, which is again just this nonlinearity thing. Now, what I want you to think about for a second is what if we had the same structure? So we repeat this many times for L different layers. The input is mapped to the output layer, and then that is then put through a nonlinearity, and then that new vector is then used as the input to the next layer until we get all the way to the end, in which case we estimate some y hat, which again, this g is this sigmoid, and so it maps any real number to something between 0 and 1. And so that would be our estimate for our probability of being labeled equal to 1. This is a binary classification problem. And then we use our same cross entropy loss that we talked about for logistic regression. Now, one thing to think about is what would happen if we didn't have any nonlinearities? What if we just use this last nonlinearity, but none of the internal ones? Because then what we would have is that y hat is like, what if no nonlinearity g applied at each layer? Well, then y hat would be equal to g of theta of L, A of L, which is equal to this G of theta of L, A of, sorry, because A of L is equal to theta of L minus 1, A of L minus 1 equal to G of theta. And this goes all the way back to theta of 1 x. But then these guys here are just a bunch of matrix multiplies together. And so what we would get is we would just get G of some other matrix, theta 0, I don't know, times x. And then all we'd get back just a linear function. And so this would be very, very not good, right? And so the point here is that having these nonlinearities at each point in the intermediate layers are what make this a difficult or a more complicated function. And they're crucial to get this very nonlinear structure. Because in general, what we have is that y hat of L, because with these nonlinearities, we have the nice sort of structure of G of theta of L, G of theta L minus 1, G of theta L minus 2, dot, 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 all the way back to x. And this composition of functions, this keep applying a function on top of a function on top of a function, the output goes in the input of the next one, is what really gives us a more nonlinear structure. And it's easy to see that you can start actually creating these XOR gates or these nonlinear sort of structures by adding, subtracting just very, very simple structures. As soon as we add just one layer of this hidden layer with this nonlinearity. Before moving on, does anyone have any questions about this, about the structure of the neural networks, how the input gets mapped to the output, these intermediate layers, the dimensions of anything?
Yeah, is the L for the layer number unrelated to the L, like y hat that looks like a loss?
Oh, yes. Sorry about that. Yeah, this L, this L has nothing to do with this L. This is the loss. This is loss, and then the other L's on this side have to do with the layer number. I'm just indexing the layers by L. But when I have L in the blue, that's a loss function. Sorry about that. Okay, and so this is using this sigmoid structure at every layer, the same one, but you don't really need to do this. You could have applied a different one, right? So like, it's important that you have this nonlinearity, but what nonlinearity you put in these intermediate layers, in these so-called hidden layers between the input and the final output can actually be pretty much any nonlinear function, but there's lots of popular ones. And what these are called, though, it's called an activation function. And there's many examples of these. Some popular ones are the sigmoid, tan H, and ReLU, for instance. But there's many of them. But the ReLU stands for rectified linear unit. And all it does is it's a function that is 0 for x less than 0, and then a ramp, ReLU of x, for x greater than 0. Very, very simple function. But what we can see is that this function is actually very nonlinear, meaning it's just not linear. Anything that's nonlinear is just not linear. So it's pretty easy to satisfy that. But the point is, you can mix and match these nonlinearities in the hidden layers, and they do have different effects, different optimization properties, different generalization properties, and things like this. But the ReLU really is the most popular these days, both because it's easier to optimize. It turns out the gradients don't go to 0, and because it's actually very fast to compute. If we use this sigmoid internal function, this requires an exponential, and exponentials are just more computationally intense than a max function. Very simple sort of reason. So that's binary classification. Through multiple classification, we proceed exactly like we did with logistic regression. It's just instead of having one output, we have, if we have k classes, we have k outputs. And then what we'll do is we'll classify, we try to apply these one-hot vectors, just like we did with MNIST on your homework, where we're trying to then output a vector, whereas a 1 on the desired class and 0 on everywhere else. And any intermediate value is just going to be some sort of confidence of how confident you are in that class. So that's how these neural networks work for classification. For regression, the story is largely the same. We still have this composition of functions. We can use arbitrary activation functions along the way. The only difference is that now, instead of putting the last layer through a sigmoid, we just output the last layer. And then we would train using a loss that's like least squares, because or the squared loss, because that's this very fundamental sort of parameter. If we want our y hat to be equal to y, you might as well just square the difference and then try to hit that metric. And so with regression, we start to see, like, very obviously, and also with classification, that these are acting exactly like the linear classification and linear regression rules. The only thing that's different is that we've added, a few different layers, a few different sort of like iterations of this process internally. And if we just looked at that last layer, we'd be exactly just linear regression. But before then, we've passed it through a number of layers. And what's going on in these layers is you can somewhat interpret these layers as sort of generating features automatically. So when Jamie was talking about these fees that you had to come up with an engineer or a kernel function engineer, what's happening here is the weights are actually transforming your data into a different, basically up to this space. You can think of all of these layers as just sort of a intermediate step to transform your input features to almost learn a fee, where that fee is mapping from your input space to the last layer. And then on that last layer, you're just applying linear regression. And this is actually how we think of neural networks. This is the modern sort of interpretation of them, is that these internal hidden layers are really just learned feature maps. Instead of just engineering a feature map fee or guessing one or using a random one, what's happening here is these neural networks are actually learning a fee. And that's how it's one interpretation of what's going on in these hidden layers. One reason why we like neural networks is that we call them what's known as a universal function approximator. And what this is saying, what this theorem says, is that if I have some d-dimensional space, and I have just a 2-layer hidden network, meaning that I have, this is my x, and then I have one hidden layer, and then this goes to just a single output y hat. Then, so let's say m hidden nodes, let's say. Then what this is saying is that for any function f that's bounded, there exists a neural network with just that looks like this left-hand side here, where the number of hidden nodes is finite, m. It could be very, very large, but it's finite. And such that for any epsilon, so you pick an epsilon like 0.001, I promise you that I can find a neural network that will approximate, there exists some finite m such that my estimated output, so instead of y hat, we'll call it f hat of x, this output, there exists some, for any epsilon, there exists some finite m large enough such that f hat m is arbitrarily approximating the true function f of x. And this is pretty easy to see. So one way to see this is that if I have any function, so if you've ever taken a real analysis course or anything like this, any function can be approximated by step functions. So I can approximate any function by, almost like Riemann integrals from, I don't know, grade school? I don't know. I guess calculus. Anyways, yeah, high school. So I can approximate any function by just a sum of step functions, right? Where each one of these is basically, I can write this as indicators of like some constant a times indicator of 1 that's like x is greater than z1 minus indicator of x greater than z2, where this is z1, this is z2, and then this value here is a. And then so basically this function can be arbitrarily approximated by a sum of these step functions. And so, okay, that's great. And so what we know from real analysis, usually the next step in this proof is to say, well, since I know that I can arbitrarily approximate a function with step functions, with a neural network, can I arbitrarily approximate a step function itself? And with ReLUs, this is very easy, actually. Because what you can do is I can have a function that looks like this, plus a function that looks like, or minus, that would be one function, and we minus a function that looks like this, but shifted a little bit, and then minus another function that looks like this, will all equal a function that looks like and then plus a function that looks like this will equal a function that looks like this. It'll look like a little bump. And so basically, these layers here, these functions, these functions are the outputs at these internal nodes. So this function here is x is coming in, let's say just one-dimensional, not d-dimensional, one-dimensional. X is coming in on the x-axis, and then at this node, we're getting this function. And 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 then I'm applying these weights, this plus 1, minus 1, minus 1, plus 1 here, so plus 1, minus 1, minus 1, plus 1, and I guess this fifth one's just 0. And that's getting my output, which is then outputting this sort of bump. And by putting different weights in there, I can make the walls of this thing sharper and sharper, and I can approximate a rect function. And this is basically how the proof goes down. Is basically I can approximate any function in d dimensions if it is a bounded function in a compact space with a one hidden layer neural network, which is a big deal in the sense that they're arbitrary function approximators. This class can approximate any function class, which is not true for linear functions, as we've discussed. This is quite remarkable. This function class is very, very general. Any questions on this? What we talked about so far.
I had a question. So can we talk about, okay, if your neural network looks like this, it's just a combination of matrix multiplications and ReLUs, right? So like what class of functions are you fitting for your data exactly? Right. So with the kernels, we talked about it's weighted, it's like weighting of your kernel function. So given this structure, which seems kind of like not the most complicated structure, like ReLUs, and matrix multiplications, like, so what are you fitting exactly? What class of functions are you fitting to approximate things?
I mean, so it's not as explicit, I guess. This is the class of functions. Like it is just the class, like you write down an architecture. So you define where the nodes are and what the weights are. And then within that, so for that architecture, you fix that graph. And now that fixed graph is a set of different functions that can be learned. And I'm saying what this theorem is saying is that if you allow yourself for the number of hidden nodes to go off to infinity or get very, very large, you can basically arbitrarily approximate any function. And so the space of functions, like typically we distinguish between, like, for a fixed neural network architecture, what is the space of functions that can learn? That is a finite space in a sense, or a compact space in a sense. But then if you allow the number of nodes to flex in some way, then that allows you to get very, very complicated. And that's sort of the kind of function. And so if you have ReLUs in this internal network, what's really going on is what you're learning, that the space of functions, this particular network is one hidden layer with one single output and ReLUs in the middle. This class of functions is, and if you allow the number of hidden nodes in the inside to flex, this is all piecewise linear functions. And so this is just like all functions that have all sort of piecewise linear. And this is what ReLUs give you. And we'll see in a second, in higher dimensions, basically what ReLU networks give you are all basically piecewise flats. These functions, you can approximate a function by a bunch of half spaces or by a bunch of planes. And it gives them for some really gnarly structures, which we'll see in just a moment.
Right.
Kevin, there's a nice question in the chat about whether this proof is true for any nonlinear activation function.
Great question. No, that is not true. It is not an arbitrary activation function. It holds for a very, for ReLUs, it is true. For sigmoids, it is true. For tanh, it is true. So like we pick the nonlinearity to have a property that would satisfy this theorem. But no, in general, if I just write an arbitrary nonlinear function like a sine wave, that's probably not going to be true. Although actually, because of Fourier series probably is true. But a
linear function that basically will never satisfy this, like maps every point to zero. That's maybe that is a linear function. But like, maps like half of your points to zero and half of your points to one in a way that's nonlinear, that's not going to have this property.
Yeah. So it does not hold for all activation functions.
I have a quick question.
Some are better than others. Yeah.
Could you explain the relationship between these hidden nodes and the graphs that you drew, those ReLU graphs, and how they like form this graph f of x?
Yeah, so the way that you should think of it is you have an input x, that's your feature vector. If you have, housing prices, x is just a d-dimensional vector, number of square feet, number of windows, etc. And then what we're going to just call that is a of 1. That's just our first layer, it's our input. And now what the internal nodes is this guy here, because this guy, for this particular network, this guy is in R3, because there's 3 nodes here. And now A2 is now 5 nodes. And so this guy is in R5. And this, this guy right here is the second dimension of that output. And so this is equivalently I equals 1 to 3 of 1 and then 2, because I'm just looking at the second output, I xi, or equivalently A1. Maybe I should do that. A1 of I. So each node in this graph is basically you take the inner product of all the nodes on the previous round or previous layer with the weights that are going into that node, and then I put it through a nonlinearity, which is sigma. Okay, and so when I input a vector x, that automatically populates a value at each node in this graph, and at the final node, this final terminating node, that's going to be your y hat. That's just a scalar. And so I put it in an x, and it basically cascades through this network, and I eventually get an output at the end.
Okay. And is the number of hidden nodes in each hidden layer, is that arbitrarily set, or is that decided by something?
Yeah, that's arbitrarily set by you.
Okay.
By the ML engineer. Yeah. Okay. Okay. So if you've heard of neural networks or deep networks, what you probably know of them is that they take a long time to train. They're very hard to train. They're very annoying to train. And there's lots of hyperparameters. And by the way, if I use the terminology deep net, if that slips out of my mouth at some time or another, all that really means is that the number of layers is large. So instead of having like 3 layers, a deep network might have like a 10 layer or 100 layer or 1,000 layer network. And really, this is the only difference. I mean, this is really the big difference between networks of today and networks of the 80s, was that in the 80s, they were doing maybe 3 layers or 4 layers, and now we talk about layers in the dozens. And there's a big reason why we couldn't do that in the 80s and why we can do it now, and why there's been this revolution. And we'll get to that. So training neural networks. So we have our network here. And the way that we're going to train this, the most basic way we're going to train this network is basically the only algorithm we know for non-closed form functions, which is gradient descent. We have our loss function, L of y hat. Y hat is a function of all of our parameters theta. Thetas are the weights of this network. We don't know what they are. They're free parameters that we need to learn. And so what we're going to do is just for each layer L, we're going to perform gradient descent on that layer. Simple, right? There's nothing really complicated going on here. All we're doing is we're doing stochastic gradient descent or gradient descent with respect to each layer. And you can even have a step size that differs by layer. That can be tricky to set. So sometimes you just set eta to be some constant, and you run gradient descent. And that's basically it. This is how you train these networks. There really is not much more than that. So if this is so simple, if we are just running gradient descent at the end of the day, you might be wondering, like, well, why are there, you might have heard of packages like PyTorch and TensorFlow, Theano, Caffe, MXNet. Why are all these packages out there to do something that is a one-line algorithm of gradient descent? Because all of these packages are designed explicitly just to train neural networks. And a big reason why is because something called automatic differentiation. And basically what this is doing is an ability to, instead of taking the gradient at each one, computing this gradient at each layer, which is actually quite complicated, as we might get to in a moment, instead, it can take that gradient automatically. And it's been this sort of revolution in something called automatic differentiation. This is different than symbolic differentiation. This is not Mathematica, where we are taking the gradient of something analytically and writing down it and then evaluating it. This is also not finite differencing. We're not sort of taking a tiny step away and then subtracting and dividing by the denominator. Those are two very different things. Really what automatic differentiation is applying the chain rule in a careful possible way to train these networks in a very efficient way, and or treat the gradient in a very efficient way and very stable way. And so basically automatic differentiation is a method for if you have a bunch of functions, G1, G2, G3, G4, etc. Basically, if you have this big composition of functions, how do we efficiently take the gradient of this function at different points at this function? How do we take the gradient of this function? And basically, we can do this by defining the gradient of each individual layer or each individual composite function, and then they all sort of stack up by the chain rule and calculus, and this is done in an extremely computationally stable way, and that's what these packages are really doing. They're implementing very, very good ways of taking derivatives of these functions in a very computationally safe way. Another benefit of automatic differentiation is that basically, and I'll get to this a little later, basically, there's not a whole lot of reason to write down your gradient yourself. And the reason why is there exists this theorem that says if computing a function takes n flops, floating point operations, then I can compute its gradient in just order n flops. In fact, five n flops suffices. And it's basically, the proof is reverse mode automatic differentiation. And basically what it's saying is that, like, if you computing the gradient of a function is computationally no more difficult than computing the function value itself. And so this has really been sort of a revolution in how you should always be taking gradients. And really, I wouldn't trust myself to take a gradient of a very complicated function these days. I always would just use PyTorch because I'm bound to make a mistake, an algebra mistake. So that's the number one reason why these packages exist. The second biggest reason why these libraries exist is because they contain lots of convenient libraries. So for a different neural network, this is a bunch of layers. This is how you build up. You define some different layers. These are the different weights that you're defining. This layer here, for instance, is basically just a matrix in 10 by 84. It's a weight matrix, and the conv layers are also weight matrices defined with a particular structure that we'll get into later. But then to actually implement this function, we have some input x, and we map the output, the internal layer, we call this internal layer x, as just, we're going to have this conv layer, which is just, again, just think of it as a weight matrix. We're going to apply that weight matrix to x. Then we're going to apply a ReLU, this nonlinear function, to that output. And then we're going to do some other nonlinear operation, or this linear operation of a max pooling. And then we're going to repeat that again, and then we're going to get our output. And so all of these functions make it just super simple if you want to have particular structures. The ReLU is already implemented, the max function is implemented, the conv layer is implemented. This is the forward pass, and very easily you can just take the derivative, you say dot backwards, and all of a sudden you have a gradient. And this is really what is the power of these functions. Everything is already implemented for you, and you can take gradients very, very easily. This is really the power of Torch and TensorFlow, etc. Also, as we'll see in a moment, there's lots of optimization algorithms beyond stress gradient descent. We've already sort of alluded to these, the AdaGrad, Atom, these sort of things. And these are just sort of more fancy ways of optimizing a function beyond stochastic gradient descent. But basically, all these methods are wrapped up in all these different functions, so that you don't need to write dozens and dozens of lines of code. You just sort of call out to a function where it's already written, it's already numerically stable. And so to do very, very complicated networks takes a very, very small amount of code. That's one reason why these software packages exist. And a third big reason is GPU support. So if we look at this network, something like this, it's a lot of matrix multiplies going on. And one thing I stressed when we were talking about linear regression is that if you're ever taking the inverse of a matrix, you're probably doing something wrong. Because if you should always be calling out to a solver in NumPy or LAPACK or BLAS, which is doing all these matrix multiplies for you. When you do NumPy dot for matrix multiply, that is not doing a for loop over like interpotting this row with this column and this row with this column and this row. That is not what's going on. They're using very, very sophisticated matrix multiplies that are extremely fast. Now, GPUs are doing this as well. So GPUs, one way of speeding up these computations is by parallelism. I can tile this matrix in different blocks and then basically compute these matrix multiplies extremely quickly. By parallelizing it, by having blocking my matrix and then sending that block in this piece of the vector to some processor or some GPU unit, another one to a different GPU core, and then they all do their work simultaneously, and then they collect back their answers in the gather operation, and then they get back the answer. And this massive parallel resources is what really has been driving the deep learning revolution, because driven by computer gamers in the 90s, we wanted faster and faster GPUs that could do many, many fast matrix multiplications. And this led to enormous computational resources to doing matrix multiplies, which are exactly what neural networks do. And so really without computer gamers in the 90s, we would not have the deep learning software or hardware that we have today. It's kind of a very strange story. And even to this day, when you buy a GPU, it has like gaming stuff on the back. And I think it's just hilarious that like these are marketed towards gamers, but now I think the market share is actually more going towards deep learning than computer games, which is just really kind of amazing. So that's what these software packages are giving you. They're giving you these three big things: the automatic differentiation, good code to do that, very safe computational feasible things, convenient libraries so you don't have to write all the same code over and over, and GPU support to actually get these things to work. So all you have to write is a matrix multiply, not worry about what it's doing in the background. You just send it to the GPU and it's gonna take care of it. The final thing that we need to worry about with neural networks, I mean, I'm saying like a lot of great things about them, right? I'm telling you that they can fit any function, they're very flexible, we have this great software for computing them, but one major problem with them is that they're non-convex. And what that means is that when I go to train one of these things, I could have a function that looks like that. That's the minimum of this loss function. And if you just run gradient descent, you might land up at a local minimum, right? If you initialize wrong. Well, optimize wrong. And escaping that local minimum is very, very hard. And so that's one major difficulty. And so there's lots of algorithms that speed up this process, try to avoid a local minima in some way. But this is a major issue. Converging to local minima is a very real thing. Another major issue is that if you look at these networks, when we talk about backpropagation, basically we'll find that if you take the gradient at this node here, with respect to the loss function, the loss is computed at the end. So basically, this loss, whatever you get here, has to get all the way back through all these layers, all the way back to this node where you're taking the derivative. And What can happen though, if there's many layers, if some of these nodes are very close to zero, if some of the weights are close to zero, it's very easy for these numbers to lose numerical precision, and they go to zero. Or another way, if all the things are multiplying by each other, they can blow up and go off to infinity. And all of this has to do with just numerical precision. If we had perfectly precise computers, this would not be an issue. It just has to do with the fact that a computer will round solutions, and it is not perfect in computation. And so what happens is that these networks can, when you take the gradient, they can blow up or go to zero. And so there's different issues. There's different ways to get around this with things like batch norm, or use different architectures like a ResNet. Because these are because these are non-convex, the step size matters. Whether you're going to converge the local minima, the batch size is going to matter. Whether you use momentum or not is going to matter. All annoying questions that we have no good answer to. Overfitting is a very weird quirk of neural networks. Is that we talk a lot about how overfitting is like a disastrous thing, and that's still true. But for reasons that are not totally understood, it's being worked out. It's a modern topic of research, but even today, we don't really understand why when you train these networks, typically we train them to 100% accuracy, training accuracy. Even if the test accuracy is only 80%. Why? And not train it so the train and tests are about the same? Yeah, it's a good question. There's some theories out there, but this tends to actually be a very sort of realistic paradigm where a good stopping condition is when you hit training error equal to zero, even if your test error is still well above zero. There's no good answers here. Another interesting quirk is that if you grow the size of your network, it may actually train faster. More parameters, more flops, but who knows? Basically, by making the network larger, you are changing the loss landscape, and you may make the function easier to optimize with more parameters. So yeah, not awesome. This is not a great story. There's choosing what network, how many nodes to put, how many layers to put, how many internal nodes to put, what nodes to put, what optimizer to use, what nonlinearity to use. These are all major issues, major questions. And really a lot of these things are chosen arbitrarily or through experience. There's good rules of thumb, but a lot of them are just chosen through hard work and time. And so this is a pretty sad story. Neural networks are incredibly powerful. They're hitting state-of-the-art performance, better than kernels. But the sacrifice here is that we went from this beautiful story of kernels, where we understand everything, we have great theory for them, they're convex, with the matrix inverse, or where the matrix solves, it's closed form almost. It's so well understood to this theory of neural networks that's much less understood. There's a lot of great research coming out, just in the last couple of years that have gone a long way towards just explaining why neural networks work or how to choose some of these parameters, but a lot of it's still theoretical and not really good enough to motivate practice. And so this is just sort of an issue where we're at right now. Yeah, these are some things. If things are not working, you should just basically change all possible parameters of this network. And now in the last few minutes, I found this awesome website that was put together by, I want to give them credit because this is just so cool. Daniel Smokov and Sean Carter. There's this website, it's linked to on the website, which is called playground.tensorflow.org. And basically it allows you to play around with a different network in real time, add more hidden layers, add more nodes, and see what happens. And so one thing I want to stress, and you can also play around with regularization. So on the left-hand side, we're trying to learn this function. So we're in a classification setting, and we're inputting our x1 and x2. That's the input. We're just in 2 dimensions here. And what we have here is somewhat of a checkerboard here, this XOR function, and we're trying to learn it. And so with just 0 hidden layers, with just x1 and x2 as input, as we discussed in class, we cannot learn this function, right? A linear boundary cannot learn this. And so when I hit play here, I set the learning rate, the activation function like a sigmoid or a ReLU, and I hit play, and it's doing gradient descent. And it's not going to be able to learn anything. And this is the training loss and test losses up in the upper right hand corner. But now if I add a hidden layer and add a few layers here, if I now hit play, it's doing its thing, it's doing gradient descent, and it's going to converge to something that's going to fit this data pretty well. And so you'll get 0 training accuracy, or it'll eventually go to 0, and then you'll have some test accuracy as well. But what's kind of cool about this feature is that you can also use this for your intuition for different sparsity and things like this. So like what I can do is I can add regularization, just like we did in linear regression with L2 and L1 regularization for ridge and lasso. We can still do that on neural networks. So we can apply an L2 penalty or an L1 penalty on all the weights in our network to do this. So suppose I didn't want, right now, all the weights are non-zero. That's what the size of the edges here are showing, that the weights have some non-zero coefficient on them, whether it's positive or negative. The size of the coefficient is the absolute value, and the color is positive or negative. But what if I applied an L1 penalty? Now what this is doing is it's penalizing L1 penalty, so I would expect a sparse solution. I should expect to get the same answer, but many more of these nodes are actually going to have 0 weight on them, which is exactly what we see. So all that intuition that we gained about linear regression also transfers over to neural networks. If we apply an L1 penalty to the weights, we should expect to get sparse solutions out. And so that's about, you can play around with the different learning rates. You can play around with different functions. And so like different sigmoids, it can eventually learn this, I think. Yeah, it should be able to. But like one thing I want to mention is that like different activation functions have different look to them. And so if I use the ReLU, what I said a minute ago was that these are going to be basically piecewise linear. And so if we try to learn this function, which it's failing to do, because I've not tuned my hyperparameters correctly, which is a major annoyance with all these sort of things, what I should get on the output of this whole thing is just a big sort of hexagonal or like polygonal sort of shaped function. And that's really what's going on in these higher dimensions. And this is eventually going to run and eventually learn to fit this function after a very, very long time. And so this is on the website. It's just a really cool sort of app to like get you to play around. And here you can really see the polygonal structure here of what these functions look like in high dimensions. And it'll eventually learn it. And so I encourage you to go and play around with this. Each internal node here is what that function is being computed at. So that inner product of the input nodes put through the nonlinearity, what's showing up there, each one of these internal nodes, is that function being computed. And so this is sort of a fun sort of thing. Might give you some intuition for like how regularization works. You can go all the way back to 0 hidden layers, and now you're back to linear. And you can play around with that as well. And so that's all I kind of want to talk about today for neural networks. They're going to come up later in the quarter as well. I just want you to be exposed to them early on before we start going to more domain specific applications like image and audio processing and things like this. And so with that, I'll conclude and take any questions that you guys might have.
I have a question about the universal approximation theorem. So, so I understand that in case of neural networks, it can learn arbitrary. It can basically learn any kind of function. But why isn't that true for kernels in case of SVM? Because it seems that they can also map any data to infinite space. So it seems like they should also be able to learn any kind of function arbitrarily.
Excellent question. So with an RBF function, that is true. So actually you can learn any smooth function. There's lots of theorems that describe this process. And so as the way to see this, at least intuitively, is Jamie showed this slide where it's like, well, if I don't regularize my kernel ridge regression, if I don't put that W2 penalty, I just get that my alpha is just going to be equal to K inverse Y. And that means I'm going to be able to perfectly predict my Y every single time. Whatever data you give me, I can perfectly fit it. And that's the very definition of a universal function approximator. I can fit any possible function in any set of X's and Y's you give me. I can hit every single Y given those X's. And so that's also true. Kernels, for appropriate kernels, not all kernels, but for some kernels, in particular RBF, you can learn any smooth function. And so this is another property why kernels are beautiful. Kernels are amazing. Like there's not much you can say that's bad about kernels, aside from perhaps being computationally intractable for large N, because what you have to do is you have to store this matrix, this kernel matrix, this N by N thing, and once we get to data set sizes of millions or billions, a square matrix of size billion is a billion times a billion numbers, and you can't fit in memory. I mean, you can't do np.solve. You just can't do it. Whereas why can neural networks scale to millions and billions of examples? Because they're running gradient descent. And we go back to the stochastic gradient descent lecture, where you